Okay, sorry we're starting a minute late. I just remembered at the last second that I wanted to grab this thing for class today. So our test is a week from Friday. I don't quite have it ready yet, but in the meantime, does anybody have any questions? We'll probably hit the cutoff, not today, but on Friday. Yep.
The start, is it just from the start of the last midterm?
We'll focus on the material that we covered since the last midterm. So whatever the cutoff of the last one is, the focus will be from there. But it's sort of not going to be strict because you can't exactly forget about everything you did before, but like the primary parts will come from since the first test. Okay, so when we hit the cutoff, hopefully by Friday I'll have the test written and I can give you some more information. So last day we did more stuff about capacitor circuits. We looked at parallel, we looked at combination circuits. That covered our capacitor circuits, and next we're going to move on to the energy storage. There is a simulation on FET. It's not really that interesting, but it's kind of fun. If you make him rub his foot on the carpet, it's supposed to make sound. Anyway, if you make him rub his foot on the carpet, he gets a shock. And if the sound worked, you'd probably hear him go ow or something. Anyway, not that exciting, but this kind of something everybody's familiar with, right? Like you scruff along a carpet, you touch somebody and you get a shock. That's the sort of thing we're going to be looking at, is the energy in that sort of thing. Okay. So when we started capacitors, we said it was a circuit device and it's used to store energy. So now we'll sort of think about how it stores energy. How does that work? So one of the first things we talked about was inside the battery, as we charge a capacitor, the chemical reaction inside the battery does work to move a charge through the battery. The charge moves through the circuit and eventually lands on the plate. So the battery does work to move the charge. And from the physics 1050, 1020 idea, we know when we do work on a system, we transform energy. So that's what's happening there. Charges keep moving, keep moving, keep moving until the plates are fully charged, until they can handle or store no more charge, and the potential across the capacitor is the same as that across the battery. So then what happens to the work put in? What happens to the energy that was transformed? The thing that happens to the energy is it gets stored in the capacitor. So the energy is stored. So two kind of interesting bits here. If it's stored energy, we know that that's electric potential energy. We know the symbol for electric potential energy is a U. What I find really interesting is where is it stored? Like in a spring, that's sort of easy to understand. It's stored in the coils of the spring. Where is it stored in a capacitor? Turns out it's stored in the electric field itself. Same thing with gravitational potential energy. When you push something up high, it has stored energy, and the energy is stored in the gravitational field. So I think that's kind of interesting. If you're interested in the derivation of the expression for the stored energy, I will write down C-text. We're not going to go through the derivation in class. It's not really one of the outcomes of this course. If we're not going to go through it in class, I'm not going to ask you to reproduce the derivation on a test, but if you're interested, you can review your text to look it up. We see that the electric potential energy stored in a capacitor is the charge squared divided by twice the capacitance. So that's our expression for energy stored in a capacitor. When we're thinking about these values, we know that C is the capacitance, and our expression for capacitance previously was A times epsilon naught divided by the plate separation. And C is also the ratio of the charge over the potential. Okay, so those are a couple of things we know about capacitance. So we can tinker with this equation a bit. We can say that Q is C times delta V, or we could say that C is Q over delta V. And we could also get that the potential energy is 1/2 times C times delta V squared, or 1/2 times Q times delta V. So there's the expression for the electric potential energy stored in a capacitor. So we'll put this in a box. Okay, any questions there? So the potential energy depends on the capacitance. So the capacitance, again, is a device for storing energy. Places where you use capacitors to store energy are often places where you need a burst of energy kind of quickly. So like, you know the AEDs, if somebody goes into heart failure and you grab one off the wall and you give them a shock, those have lots of capacitors that store up energy and get a quick delivery. Another example would just be the flash on your camera or your cell phone. So that flash uses a lot of energy really quickly, and that energy is stored in the capacitor. So let's do a couple of examples. So for the first one, let's use that flash example. I guess maybe not tons of people use this kind of camera anymore, but lots of people do use their cell phone camera with a flash from time to time. So let's say we've got a capacitor inside a camera flash, and it's got a capacitance of 220 microfarads. So C is 220 times 10 to the minus 6 farads. It's been charged to 330 volts. That's our delta V. How much energy is stored and what is the average power dissipation? So let's do the energy part first. So define the energy stored. That's U. That's what we wrote on our previous slide. So we know C and delta V. Let's use this expression for our power to calculate our power. Oh, not sorry, power, our energy. So potential energy is 1/2 times C times delta V squared. 1/2 times 220 times 10 to the minus 6 farads times 330 volts squared gives us an energy storage of 12 joules. That's kind of a lot of energy stored. And so that's how much energy has to be stored to get a flash on the camera. And then the thing we often care about, so I said we often use these capacitors in places where we need a quick discharge. The amount of time it takes in comparison to the energy used, that's something we rate with power. So let's ask, what's the power dissipation? So as a reminder, power is the change in energy divided by change in time. So let's say we dissipate all of the stored energy, 12.0 joules. And it takes 1 millisecond, so most of these bursts are really fast, like 1,000th of a second. That gives us a power of 12,000 watts. That is a lot of power at one time. So as a reminder, P is our rate of energy transfer. Okay, questions? All right, let's go through a couple more examples. So for our next example, let's do kind of a simple model. Oh, here's where I wanted to use this thing. So when I brought in the Van de Graaff, we held up the two spheres and we made little bits of lightning. We can do that with this little Van de Graaff generator too. This is really a neat device. What happens is I turn the crank. As I turn it, energy starts to come out of the air, goes onto the wheels, gets stored in these little jars, and when you get the field big enough, it jumps from sphere to sphere. So as soon as that electric field hits about 3 million volts per meter, the air breaks down, becomes conducting, and the electricity travels through the air. It's not an insulator anymore, it's a conductor. So this is a miniature version of lightning. This is what happens when the clouds store up so much charge that we get a big electric field between the cloud and the surface of the earth. Then the air breaks down, we get dielectric breakdown, and we get the big spark traveling from the cloud to the ground. That's lightning. So this is miniature lightning, just like we looked at with the Van de Graaff. Yep.
Would the power dissipation on the battery of the camera be negative, the power dissipation of the flash?
So the
Because the battery's losing that amount of energy that's expended with the flash.
Well, that's the energy that comes out of the capacitor, and then the battery will, over time, recharge the capacitor.
Okay.
And it's probably going to be a different power, like it'll take a different amount of time. It recharges slowly, and it dissipates quickly. Yeah. We'll talk more about that when we get to RC circuits as well. Okay, so the charge center of a thundercloud, the cloud we're saying is 3 kilometers above the Earth's surface. We say that the cloud is carrying 20 coulombs of negative charge. 20 coulombs is a lot of charge, so that's a big charge. Assume that the charge center, so the cloud has a radius of 1 kilometer, and we're going to model the cloud and the Earth as a parallel plate capacitor. So let's get a sketch of what's happening here. We've got a big cloud. We're going to assume it's more or less round. It's got a radius r equals 1 kilometer. There's our radius. There's the surface of the Earth. The cloud is 3 kilometers high, so that's our distance d, our plate separation, 3,000 meters. And the net charge on the cloud is negative 20 coulombs. Okay, negative because it says it has negative charge. The other number we're going to need in this problem is epsilon naught 8.85 times 10 to the minus 12 coulombs squared over newtons meters squared. So let's treat the cloud and the surface of the Earth like a parallel plate capacitor, and let's figure out what would be the capacitance of this model. So this is kind of interesting. So capacitance is a feature of the physical properties. Capacitance is the area of the plates of the capacitor times epsilon naught divided by the plate separation. We're assuming this is round, so we're going to say pi r squared. So I've got pi times 1,000 meters squared times epsilon naught. Divide that by d. And we get a capacitance of our model of a capacitor to be 9.27 times 10 to the minus 9 farads. So we said in general capacitances are pretty small, and this is actually a pretty small capacitance. It's still times 10 to the minus 9. Okay, any questions here? So this part is fine. Find the potential difference between the cloud and the ground. So we want to find delta V. So the size of the potential difference, delta V, is going to be the charge divided by the capacitance. We know that there's 20 coulombs of charge divided by our capacitance, which gives us 2.16 times 10 to the 9 volts. That is a very high potential, we will say low. Okay, so that's a big potential difference between the ground and the earth, or the cloud and the ground. So we've got a potential difference. It's between here and here. We know that distance. So how big is the electric field between the cloud and the ground? So that's another good thing that we can calculate. So our electric field E is the potential difference divided by the separation between the plates. So our potential from part B divided by our separation, that was 3 kilometers or 3,000 meters. That gives us an electric field of 7.19 times 10 to the 5 volts per meter or newtons per coulomb. So there's the electric field. That's a big electric field. In context of lightning, we get lightning when the electric field is about 3 times 10 to the 6 volts per meter. So we're close, but we're not at lightning territory yet. And how much energy is stored in this system? So the amount of energy, we know a lot of stuff. We know the capacitance, we know the potential, we know the charge. So we could use any of these equations to calculate the energy. I'm going to use a half times Q times delta V. So a half times 20 coulombs times delta V to give us 2.16 times 10 to the 10 joules. So 2.16 times 10 to the 10 joules. If you look at that number, you probably say that's a big energy. But let's try and give it a little bit of context. How much energy is it? So this is the amount of energy stored in a field, kind of a little bit before we get a lightning strike. Okay, if we store a little bit more charge, we're going to get a bigger potential, a bigger field, and we're going to get that lightning strike. So to put it in context of energy, I looked up on the Newfoundland Power website, what is the average power consumption of an average Newfoundland family? I didn't look up what an average Newfoundland family is. It's probably, you know, a couple of parents and 1.5 kids or something. So an average family in a Newfoundland home. So the Newfoundland average power consumption is about 1,300 kilowatt hours. So that's the power. Let's figure out how much energy is associated with this power. So this is kilowatts times hours. So this is going to be 1,300 times 10 to the 3 watts. And an hour is 3,600 seconds. Okay, so there's the amount of power. They call this power. Power is measured in watts. This is actually energy. Like a kilowatt hour is power times time. That's energy. So a watt is a joule per second. So we take the watts times by the seconds, we get the joules. 4.68 times 10 to the 9 joules. So this is sort of neat. There's about 10 times more energy stored in one thundercloud, between one cloud and the earth, than most Newfoundlanders' homes use in a month. So that's sort of interesting. I think a neat theoretical concept to try and design would be, could you design a capacitor circuit that would capture that energy? Like, could you capture that? Like, we get a lightning strike. Is there any way you could divert that into a set of capacitors? Because I can tell you, one lightning strike is going to power like a fair bit of consumption for a population. So I think that's kind of interesting.
Are people trying that right now? Have they tried to use lightning bolts for energy?
So far, it's impossible
Right.
because that's a lot of energy in a very short time. Like a lightning strike is fractions of a second for a massive amount of energy.
Right.
So I'm not exactly sure how you would design a new capacitor, because you'd have to get a new sort of capacitor and then make a big network of capacitors with resistors to be able to take all that energy in that short of a time.
It'd be like kilometers long.
Yeah, like you have this huge circuit. I think it's a good idea. I don't have the know-how to design that, but I always think somebody, one of these days,
Yeah,
sitting in
you
this
make it.
class is gonna be the person who can figure that out. Okay, because a lot of the problems facing our world today is all about energy, right? So if you could harness these natural energies, then you're the person who solves climate crisis. It's a good goal. I wish I could do it, but that's not where I am in my life. Okay, next example, let's use one of these AED things, just so we get to thinking about how capacitors work as well. So a defibrillator unit, an AED, typically we call them, an AED. It has a 150 microfarad parallel plate capacitor, which is charged to 2100 volts. So the capacitance is 150 times 10 to the minus 6 farads. The potential difference is 2100 volts, and the capacitor plates are separated by 0.05 millimeters. So then some standard questions. How much charge is on one of the plates when it's fully charged? So let's take our information and let's find Q. So for part A, what is the charge? We know that Q is C times delta V, 150 times 10 to the minus 6 farads times delta V, 2100 volts, gives us a net charge of 0.315 coulombs. That's a pretty big charge, but these things are designed to have big charges. Here's something we haven't really talked about before, the size of the plate. So let's calculate the area of the capacitor plates, and let's see what we think about that. So we know that capacitance is A times epsilon naught divided by D. A is the thing we're trying to find. So A is going to be the capacitance times the plate separation divided by D. So C times D divided by epsilon naught, 8.85 times 10 to the minus 12 coulombs squared over newtons meters squared. The area of those plates is 847 meters squared. Okay. What do we think about the size of those plates? That's not very sensible, right?
Square, wow.
Okay, so we've got 847 meters squared. So what is that, like 30 meters by 30 meters? So how this works, because you will get a bigger capacitance when you have a bigger area. So it is good to get a big area and a small separation. There are a couple of problems with small separations, especially if you just have air between the plates. So for my model capacitor, what I did was I just got two pieces of foil sheets. If I take these foil sheets and put them really close together, one thing that can happen is the plates can touch. And as soon as they touch, it's going to short circuit and you're going to get current transferring. So as soon as they touch, the entire capacitor breaks. So one thing they do, and we haven't covered this yet, we'll come back to it if we have lots of time, but if you put something between the plates, that something is called a dielectric. If you have a thin sheet of an insulating material, now you can put the plates really close together, right? So you can get them closer than you can if there's just air between the plates. So if you insert a dielectric, this D can get even smaller. The other thing that happens with a dielectric is this epsilon naught, that stands for the permittivity of free space. If you have a dielectric, those values are actually bigger. So the dielectric also changes this constant, which allows a bigger capacitance. And then the last thing we do, this is on the tech front, if you have your dielectric between the plates, and you get some layers on the outside of the plates, this is still pretty big. It's not 30 meters by 30 meters, but one simple way you can make it smaller, physically smaller, is just to roll it up.
Does it still hold the same amount of charge?
Yep, still holds exactly the same amount of charge. So now, if I roll it up, it is a smaller device, and the plates aren't touching, and it has a bigger capacity. Yeah.
When you put dielectric material, the epsilon changes from free space to the permittivity or whatever.
Of the material, yeah. So when you look at capacitors in circuits, like I brought in that circuit board one time, you see that all the capacitors are round. This is why they're round. So they're sheets that are rolled up. So that's more about device making, but it's kind of good to be able to think about those things as well.
So even rolled up, it's not like it wouldn't be anywhere near that size. It would be the dielectric causes the division to be larger.
Yeah, like we'd make it so much smaller. So we would increase this value, that decreases A, and we could decrease D by a lot as well, which would also decrease A. Yeah, so that's how we make the devices smaller. We make D tiny and we make epsilon bigger. So then this area gets smaller. Okay, and then any more questions about that before we go on to part C?
How
Yep.
big?
Oh.
Where you're going to be shocking a person
Yeah.
that completes the circuit, so would it look at the person as the permittivity of that space in between?
That's sort of different. The person is the thing the circuit is going through. So like you get one paddle here and one paddle here, and the circuit goes through the body from there to there. The person becomes like the resistor of the circuit, and we'll do resistors in the next chapter. Yeah.
What's the biggest capacitor that would exist?
We certainly have farad capacitors up in the second year labs, so I expect they get pretty big.
Like physically, would it be like meters? Or like?
That I'm gonna have to look into. Like the biggest one I've ever seen is like as big as my pinky.
Oh.
Yeah, but I don't work in
That's for,
electrical
like,
engineering.
That's for practical uses though, like if it was like industrial, like how big could they get?
Yeah, I'll have to look into that. It's an interesting question. But I expect they'll get pretty big. Okay, part C will take us back to energy. What is the stored energy in the electric field when the capacitor is fully charged? That is some bad grammar. That R should be an is. Sorry about that. Part C, so the stored energy U is 1/2 times the capacitance times delta V squared. 1/2 times, what was our capacitance? 150 microfarads. Times the potential difference, 2100 volts squared. So the stored potential energy is 331 joules. So lots of energy stored in that device that's delivered to the person and hopefully makes them feel better. Questions? Okay, so that finishes up our capacitor chapter. And next we get to start on more circuits, but all about resistors and currents and batteries. So as we start our next chapter, I'm going to, because there's so much material in Physics 1051, I'm going to pull the most important bits out of chapter 25. That'll give us a good base for the rest of the course. If you're interested in the background, you can read through the text. And I'm sort of assuming that you're just familiar with words like current and resistance. Okay, so I'm assuming you know those words, but we'll still go through all the basics. So we'll start with chapter 25. Everything we've done up until now, we've been looking at conductors and electrostatic equilibrium. That was sort of the heart of chapters 22 and 23. Now we're moving into circuits that we're gonna be charging and discharging things, so this is gonna be moving charges, so this is our chapter that's gonna get us into current. We have circuits sort of everywhere, so all of your electrical devices, of course, are full of circuits. You know, kids with flashlights, boards and computers. It's also sort of interesting that there's current flow in all of the biological systems. Like your nervous system is just one huge electrical circuit, so that's kind of interesting too. So circuits and currents are everywhere, so we're going to be talking about that for a little while. So here's a pile of background. This first box is what we talked about in chapters 22 and 23, parts 24. Conductors in electrostatic equilibrium. We saw that there was no electric field whatsoever inside the conductor, so the field inside was zero, and the charges inside the conductor didn't move. So that was our premise for a conductor in electrostatic equilibrium. So if we thought about a piece of wire, we know that inside the wire there's a bunch of charges. When we say it's an electrostatic equilibrium, it's not truly still. So the molecules inside a piece of material are never still. It doesn't happen until like you hit absolute zero or something crazy like that. What happens with these molecules and the charges is that they actually bounce back and forth a little bit. So they move up and down, back and forth in random motion. And the path that's traced out here, I got this textbook, this picture from your book. The path it will take is just random. It'll bounce up and down, back and forth, but if there's no electric field, ultimately it won't go anywhere. It'll bounce back and forth and stay put. It'll just be random motion. So that's what happens in electrostatic equilibrium, is this blue path. In this chapter, we're going to change things up a bit. We're going to take our piece of wire. So up here was a conductor, a piece of copper wire or something. We're going to take this wire and we're going to apply a potential difference across the ends. We're going to connect it to a battery. So one end will connect to one end of the battery, the other end will connect to the other end of the battery. There's a potential difference due to the battery. That's the positive side, that's the negative side. A conductor might have a length L. So this will put a potential difference across the wire. If we have a potential difference across the wire of length L, we're going to get an electric field inside the wire. Okay, so when we apply a potential difference, we are going to get an electric field inside the wire. When we have the field inside the wire, the charges are now going to feel an electric force, because force is charge times field. So there is an electric field inside the wire. The magnitude of the field is the potential difference divided by the length of the wire. The charges inside the wire are going to feel an electric force, because force is charge times field. So now what happens to each of the charges, and that's our red path here in the diagram. The charges are still going to move around. They're still going to bump back and forth and collide with other things inside the wire. But ultimately, since there will be a net force on them, it will show some net motion. So our negative charges will feel a force to the right. So ultimately, the charge will move a little bit to the right. When we talk about how fast it goes, we label that speed v with a d on it, and we call it drift velocity. Your book does a lot of background analysis of this drift velocity. That's not one of the things we're looking at in this course, so I'm not going to go through that much, but if you're interested, you can certainly read about it. So the charges do move, they have some average speed, and they move because there's a force, and there's a force because there's a field. Okay, next, when we talk about moving charges in a wire, we know that we're talking about electrons flowing through the wire. Electrons are not the only moving charges we can have. So in conductors, it is definitely the electrons that move around. And typically we call a moving charge a charge carrier. So electrons are the one we're familiar with. But if we have a plasma, the charges that move around in a plasma are actually positive ions. So it's not always electrons. So we get positive ions moving around in plasmas. And semiconductors, I find this really fun. The thing that moves around in semiconductors is called holes. So the absence of an electron is the thing that moves around in a semiconductor. If you find that a neat idea, you might like physics 3000. So that's the physics of semiconductors. That's pretty interesting. Okay, so that's kind of a recap of why the charges move. Because we put a potential, because of the potential, it feels a force and it'll start to move.
So plasmas, like the substance plasma?
Yeah.
Or is completely just ions?
The ions are the things that move around in plasmas. Yeah.
What is the liquid part? Just like whatever it is?
Yeah.
Okay.
Okay, so we are going to focus in on charges moving in conductors. So this is the bit we're going to look at in this course. When we talk about moving charge, that's current. So here's where we get to our definition of current. Electric current is the motion of charge from one region to another. So you have a bunch of charges and it moves from one spot to another spot. It's sort of important to recognize that when you flip your light switch or you connect something to a battery, the electron doesn't actually travel from here to here, the length of the wire. That's not how it works. The entire wire is full of electrons, and they all get pushed forward a little bit. Like if you had a tube full of marbles, they all push forwards. Because from here to here is a long way for an electron to go. So that's kind of fundamentally how it works. The flow of charge depends on a bunch of stuff. It depends on how well the charge can move through the material. It depends on the density of the charge carriers, so how many free electrons are there available to move. It depends on the size of the charge carrier. It depends on how fast they move, which will depend on the field and the potential. And it depends on the area of the carrier, so it depends on a bunch of stuff. When we talk about symbols, current has a symbol, typically of an uppercase I, but occasionally a lowercase I. So you're probably used to the uppercase I, it's what I'll mostly use, but sometimes you'll see lowercase. The units for current are amperes, or if you're cool, you call it amps, so amps is acceptable. That has a symbol of A, that's after André-Marie Ampère, who was a French physicist in the late 1800s, I think. Okay, so that's where the units come from. The definition of current is the rate at which an amount of charge passes through a surface with area A. So if you have a long wire, say your wire looks like this, to measure your current, you ask how much charge passes through one face over time. So that's how you calculate current. That gives us a definition. Average current is the amount of charge passing in the amount of time. So this would give us the average current if you knew the total amount of charge that moved through in the total amount of time. Sometimes charge, the flow of charge, it's a function. So an instantaneous electric current would be the derivative of the flow of charge with respect to time. So if you knew your charge as a function, you take the derivative with respect to time, that gives us our current as a function of time. Here's where your book gets a little bit interesting. Your book makes a note that says current has a direction, but it is not a vector. That throws me a little bit. To my mind, that's the definition of a vector. A number with a direction is a vector. So your book says current is not a vector. I say it is a vector. That is a hill I will die on, but you are free to make your own choices. So it is important to recognize that the current does have a direction, and the direction of current flow is whichever way a positive charge will move. We know, of course, that when you hook a wire up to a battery, it is the electrons that move, the negative charges. People were studying currents before they knew about electrons, so they assumed that the thing was moving was positive charge. They then figured out they were wrong, but at that point all the books had been written and they didn't change the books. So we still go with that convention. So that's just a modern convention. Okay, any questions to here? I still sort of feel like I'm not telling you anything you don't already know. Okay. But stop me if I'm going over something too fast. Yep.
Is it not considered a vector because none of the forms defined involve a vector?
You got me.
Alice, there's no change in direction, maybe.
Yeah, but the charge either flows right or left, right?
Yeah.
It's either forward or backward. To me, that's a direction. Right? It's either this way or this way.
Direction of magnitude.
Yeah. Your book doesn't justify why it insists that it has a direction and doesn't have is not a vector. But then it makes a leap and all of a sudden it calls something derived from current a vector. We'll get to that on the next slide. Okay, so let's just do a quick example of this, even though it is pretty straightforward. Let's come back to the lightning example. So during a lightning strike, we can get currents as high as 25,000 amps. So that's the lightning traveling through the air down to the ground. So we can get a current of 25,000 amps. That is a very high current. And a lightning strike lasts for about 40 microseconds. How much charge is transferred from the cloud to the earth during a strike? So the current is the change in charge delivered over the amount of time. So the amount of charge delivered is going to be the current times the time it takes, 25,000 amps, times 40 times 10 to the minus 6 seconds, gives us 1 coulomb. Lots of charge. Okay, still good. We won't do lots of examples of this because frankly it's just hard to think of anything interesting to do with I is Q over T. So we'll keep going with currents and electric fields. And now the next bit we're going to come to, I think, might be a little bit of a new definition for people. So the next thing we define is something called current density. So we said the current is the charge flowing past an area in an amount of time. With current density, we account for that area. So current density per cross-sectional area is called current density. It has a symbol of J. Your book very clearly defines this one as a vector. It has units of amps per meter squared. And current density J is current divided by area. So I don't know how J is supposed to be a vector if I is not a vector, but there we go. And the direction of current density is the same as the direction of current. Okay, so this one is your current density. So I think current density is new for people. I don't think that's a high school topic. Okay, or at least nobody remembers it anyway. So you may or may not remember Ohm's law from high school physics. When Ohm did his experiments, the thing he experimented on and the thing he discovered was that current density J was proportional to the electric field established across the object. Okay, so this was Ohm's experiments. Since it was proportional, you can write that J is some constant of proportionality times the electric field. So this is our first version of Ohm's law. The first thing I'll mention is that this applies to some materials only. So this is true for what we call ohmic materials, and those tend to be conductors. It's not true for a lot of other things like LEDs and semiconductors. Okay, so this is only true for some materials. So we'll say mostly for conductors. constant of proportionality sigma, this is what we call conductivity. So conductivity has a symbol of sigma, and it's the constant of proportionality between the current density and the field applied across the conductor. The units of conductivity are amps divided by volts times meters. And what conductivity tells us is how easy it is for currents to flow through an object. And we know that current will flow easily in materials with a high conductivity. So if something has a high conductivity, that would be like a conductor. It's easy for current to flow. If it has a low conductivity, then current doesn't flow, and that would be an insulator like wood or plastic. Okay, we also take this one step further. If J is equal to sigma times E, then E is equal to 1 over sigma times J. And then we define a new thing. The symbol rho, Greek letter rho, is 1 over sigma, and that's called resistivity. So the electric field is resistivity times current density. Rho is exactly the inverse of conductivity. So if we have a low resistivity or a high conductivity, current flows easily. Those are insulators. If we have a high resistivity or a low conductivity, current does not flow easily. Those are insulators. Conductivity and resistivity are what we call material properties. So every hunk of aluminum, every hunk of wood, every hunk of brick always will have the same conductivity or the same resistivity. Like no matter how big of a piece of copper you take, a big piece and a small piece will all have the same conductivity. So it depends on the material itself. Okay, 2 minutes left. I don't think we can get through the next slide. The next slide, what we'll open with on Friday, that'll take us to the familiar form of Ohm's law, V equals IR. So that's where we'll start on Friday.